This engine has a valve in the piston, which was automatic and operated without any type of command. It didn't require chains or camshafts. It was enough to have two counterweights with a spring to allow its opening and closing. It was large, basically all diameter of the piston, which allowed an ultra-fast exchange of gases. We'll also explain this L-shaped ring and why the entire engine rotates while the crankshaft remains stationary. Today's engine is the French Gnome, and with its rotating cylinders, it was the most used design in the First World War. A German version would power the Red Baron's aircraft. Today, when we say rotary engine, we think of the Wankel, but the reality is that this term initially belonged to these engines. In 1908, the Seguin brothers presented the engine at the Paris Air Show, capturing the attention of the entire world. The advantages were clear. At that time, engines produced little power and, in addition, required very heavy flywheels for optimal operation. Weight is the greatest enemy of an aircraft. The Gnome eliminated the flywheel by replacing it with the weight of the crankcase and the cylinders themselves. Vibrations were less than those of a conventional radial engine since the pistons also rotated. With an 8-liter engine, 7 cylinders, and big intake and exhaust valves, long stroke, and a compression ratio of 5:1, it initially produced 50 horsepower at 1500 RPM. The Ford Model T had a 2.9-liter engine and produced 20 horsepower. If we make the comparison with the T by enlarging the engine to 7 liters, it gives us similar power numbers, although it needs a radiator which has coolant that increases its weight. The Gnome, when rotating, ensured a huge amount of high-speed air that cooled the cylinders, making it lighter, which made it ideal for aeronautical use. The propeller rotated fixed with the cylinders. At that time, not much was known about propellers, but it was known that the tips should not exceed the speed of sound. In addition, the diameter is limited by the height of the plane to the ground, which meant that 1500 was the ideal speed. The rotary engine proved to solve all the problems that other engines of the time had by being completely reversed. Let's see in detail how it works. First, we have the hollow crankshaft that's attached to the aircraft. At the beginning is the carburetor. Inside the crankshaft, the mixture travels to the crankcase, and also there are pipes that carry oil to release it inside the engine. As we can see, the entire crankcase acts as an intake manifold and contains the mixture of air, fuel, and oil. The crankcase is connected to the crankshaft by means of bearings, which allows it to rotate freely. Then we have a master connecting rod and several slave connecting rods. Each connecting rod drives one piston, which also has an automatic valve. This automatic valve has a system of counterweights and springs, and when it goes up and then turns down, the vacuum opens it. Then, when it turns and begins to go up, the inertia and the compression closes the valve. Now we add the finned cylinders. At the top of each cylinder, there's a large valve, mounted on a threaded system that allows it to be easily removed for maintenance. This valve is controlled by rocker arms and rods. The camshaft is hollow and rotates on the crankshaft at half the engine speed. It's driven by gears. If we pay attention to the cam follower, we can see that it is completely circular surrounding the cam. It looks like the letter D. This makes it act like a Ducati desmodromic system, where it opens and closes the valve at the same time. This is because the valve is large and the whole assembly is very heavy. Remember that everything rotates and is subjected to centrifugal forces. A bad balance in the mechanism could cause the valve to open at high RPM, but with this system, this is avoided. To help with expansion tolerances and such, the valve also has a spring to keep it closed. Each cylinder has its spark plug, then a wire connects it to the ignition system. The carburetor always operated at 100%, although it has a regulation to adjust the air and try to find the ratio between air and fuel to make the mixture. The reality is that the butterfly valve did not serve to control the speed of the engine. This is because the nozzle that released the fuel was primitive and did not spray the mixture well. It also did not have a float chamber or a venturi. The carburetor had to operate at 100% to work acceptably. The mixture could be set a little off from ideal to slightly reduce the speed, but the quick way was to block the spark jump. The pilot could press this blip switch and shut off all cylinders. Obviously, the deactivated cylinders still receive fuel that will not burn and go out through the exhaust, wasting it. Power regulation was only used for landing. The engines had little power and planes were not fast enough to need to reduce it, so they went full throttle. Now, is this engine 2 or 4-stroke? I'm going to freeze the crankcase and allow the crankshaft to rotate so it's easier to explain with a single cylinder. Well, the mixture enters through the hollow crankshaft. As the piston descends, the vacuum generated causes the intake valve to open and the mixture to enter the cylinder. As it passes through the bottom dead center, inertia and compression closes the valve. The compression ratio of 5:1 is achieved and the spark is fired. The high combustion pressure keeps the intake valve closed. The exhaust valve then opens and the burnt gases escape. Now the cycle repeats itself. Intake, compression, combustion, exhaust. As we see, it's a 4-stroke engine. If we look at the engine from the outside, we see that ignition always occurs in the upper piston. It's one cylinder yes and the other cylinder no. This is because the 4-stroke engine needs 2 revolutions to complete the cycle. On the left side, we have the combustion and intake. And on the right, the compression and the exhaust. The firing order is odds first and even second, being 1, 3, 5, 7, 2, 4, 6. Here you can see better how the piston goes from top dead center to bottom dead center, and now it goes up. This view allows you to see everything more clearly without things that get in the way. Due to the primitive oil system, the engines used bearings everywhere. Now, why did the piston have this L-ring? The fin cylinders were made of nickel-plated steel, weighing less than 5 pounds or 2 kilos each. The thickness was only 0.1 inches or 2.5 millimeters. With thermal expansion and wear, the cylinders become deformed, and after 20 hours of use, all of them had to be replaced. But with the L-ring, it was flexible, helping to catch the combustion, pressing and adapting to the irregularities of the deformed cylinder, sealing and maintaining high compression, raising the useful life to 80 hours of flight. The problem with these valved piston engines was that sometimes the counterweights would jam and the engine had to be disassembled. So later, the valve was replaced with a standard piston and ports were done in the cylinder. Now, the engine would be called single valve or Monosoupape in French. This engine has the ports at the bottom. The piston descends, creating vacuum, and when it reaches the ports, the accumulated vacuum forces the rapid intake of gases. But there's a problem. In the combustion stroke, when it reaches the bottom, the fire can spread through the ports to the crankcase, which is full of mixture waiting to enter. This then causes the entire engine to explode into 1,000 pieces. Remember that it was built of very thin and light steel. To solve this, the exhaust valve opens extremely early. Since it's very large, it allows all the exhaust gases to escape. When the piston reaches BDC, there is no pressure and no risk. Then the piston rises, emptying the few gases that still remain. At night, since there's no exhaust manifold, this process allows you to see the fire coming out of the cylinders. This also reduces the engine's power since the combustion stroke is not fully absorbed. Anyway, it's more reliable than the engine with a valve in the piston, increasing time between overhaul. You may have noticed that the 36 ports are very thin. Remember that the cylinder was 2.5 millimeters thick. Therefore, since the engine could not be fed through here, the solution was that after the exhaust stroke was complete, you had to maintain the valve open to allow fresh air to enter. When reaching 2/3 of the stroke, the valve closes and the engine creates vacuum. Upon reaching the ports, this vacuum sucked in as much of the mixture as it could. It should be noted that this mixture was ultra-rich in fuel, so it would then be mixed with the existing air and balance. As you can see, the engine's only valve performs both exhaust and intake, hence the name Monosoupape or single valve. Other versions solved this with ports that went outside the cylinders. Later, an intake valve was added to the top with an intake duct, giving rise to the Rhone engine. It was notable for having a single rod to operate the 2 valves. A rocker arm would swing back and forth, pressing one or the other valve, saving weight. With 9 cylinders, power would increase to 90 horsepower. This engine could now be controlled by throttle on the carburetor, which improved fuel efficiency. A German version of this engine would be commanded by the Red Baron during the First World War. Aircraft with this engine, due to the gyroscope effect of the rotating cylinders, tended to turn quickly to the left, but very slowly to the right. Oil and fuel consumption was high, and the plane was only effective on short flights, since for the long ones they had to carry more fluids and lost the advantage of the low weight of the engine. In this video, you can see how everything behind is left shiny due to being soaked with exhaust oil. Also, by using the blip switch, you could make the plane get soaked in fuel, plus some flames coming out. The wooden plane could catch fire. The Gnome engine consumed 2.5 gallons or 10 liters of castor oil per flight hour. Castor is a type of thick natural oil used to lubricate engines, and from this derives the name of castrol. This engine has similarities with a two-stroke engine, such as using the crankcase to hold the mixture and burn oil, and even the ports. But for a radial engine to be two-stroke, it would need at least a compressor or a turbo to pressurize the crankcase to be able to do the intake. In the four-stroke, it's the piston going down that creates vacuum. And in case the two-stroke doesn't use a turbo for intake, it must have an internally separated crankcase for each cylinder, almost impossible in a radial. Later, rotary engines were replaced by fixed radial ones, since with the increased power in the years to come, not consuming oil, better understanding of air cooling, and greater durability ended up being better than rotary, making them fall into oblivion. However, they were the right answer for that specific era, and to this day we're mesmerized when we see these engines revving like crazy. At that time, there was also a motorcycle with a small rotary engine fitted to the front wheel. There were also versions with roller cam followers. If you made it to this part of the video, don't forget to leave your super thanks, like, and share the video with your friends. You can also write what you think about it. My name is Francis, and I'll see you in the next video.